this is the lesson video for physical science for section 11.3. And so keep in mind, if you want an easy way to have all my lesson videos in one spot, just subscribe to my channel and they'll all be right there. Alright, so in section 1 we talked about the difference in distance and displacement. In section 2 we talked about the difference in speed and velocity. And so now we'll talk about something very related to speed, and that is acceleration. So the rate at which velocity changes is called acceleration. So acceleration can be described as changes in speed, changes in direction, or changes in both. So keep in mind, remember how we talked about velocity includes a direction, and so even if you change direction, your velocity is changing. Well, if you change direction, your acceleration is also changing. Okay, so if you're going around this tube, say, or this roller coaster, of course we know speed would be changing too. But say it kept a constant speed, that direction is changing, so it's still considered to be accelerating. A lot of people only want to say something accelerates if it has a change in speed. But remember, a change in direction also counts. So acceleration can either be an increase or a decrease in speed. When it's a decrease, we tend to call it deceleration, and that's of course when an object is slowing down. Okay, but both of them are technically also referred to as acceleration. It's just when it's slowing down, we usually give it a negative number. So free fall is the movement of an object towards the earth solely because of gravity. So like when you're skydiving, that is a free falling. Nothing is propelling you, you just jumped out of the plane and you're just letting gravity take its course. Objects falling near Earth's surface accelerate downward at the rate of 9 meters per second squared. So what I want you to notice is when we're talking about acceleration, it's no longer just meters per second, it's meters per second squared. That's the difference in the units for velocity and for acceleration. So although you may have a constant speed, a change in direction means you're accelerating. So if you're on a big carousel at the fair or at the mall, even though it's going that same slow speed around and around, you are constantly changing direction. So technically, your velocity is changing and you are accelerating, even though you're not speeding up. That's the thing you have to get out of your mind, is we usually use in normal terms accelerate to mean we're speeding up. But in science, remember, a change in direction is also acceleration. So constant acceleration is a steady change in velocity. That is, the velocity changes by the same amount each second. So let's say here we're going 0, then after 10 seconds we're going 10, and then after 10 more seconds we're going 20. That is a constant acceleration. After 10 more seconds we'd be going 30, like that. That would be an example of constant acceleration. So like if you're in a car, it's when you just kind of steadily push the gas and you just speed up at a constant acceleration. You calculate acceleration for a straight line motion by dividing the change in velocity by the total time. The SI unit for acceleration is meters per second squared. Can't forget the little squared. So acceleration is change in velocity over total time. Change in velocity, change in science is always final minus initial. That's where you have to be careful. A lot of you want to do initial minus final. So it's final velocity minus initial velocity over your total time. Sometimes I'll write it as VF minus VI over T, but sometimes I'll just do the triangle. Okay, the triangle means changing. You probably used it in math when you did slopes. You would do change in Y over change in X. You would do triangle Y over triangle X. The important thing to remember is change in is always final minus initial. Final minus initial. Even if it's going to give you a negative number, that's okay. It's final minus initial. So let's look at one together. So it says a ball rolls down a ramp starting from rest. If it's starting from rest, is it moving? No. So our initial velocity is 0 meters per second. Okay, if it says anything about rest, that's 0. So we're starting at rest, so that's our V initial. After 2 seconds, so there's our time, its velocity is 6 meters per second. So here is our final velocity. What is the acceleration of the ball? Okay, so we know acceleration is V final minus V initial over time. So then I just plug in. So my V final, 6 meters per second. My V initial is 0 because it said we were at rest. And my time is it took 2 seconds for this to happen. Alright, so the thing is about this, seconds does not cancel because this second is in the denominator. This second is also in the denominator. That's how it becomes seconds squared. Okay, so 6 minus 0 is of course 6, divided by 2 is 3, and so I get 3 meters per second squared. Okay, so don't forget the squared. I'm super big on units, and I will notice if you leave off the squared. Alright, so hopefully that one wasn't too bad. Let's look at a couple more. Alright, so it says a car traveling, and remember, as always, you may want to stop and pause it and try these on your own. Or watch me do one more and then try the last one. But make sure you try it on your own. You can't learn very well by just watching me do it. So it says a car traveling at 10 meters per second. So this is our initial. Starts to decelerate steadily. It comes to a complete stop. So that means our V final is 0 meters per second. Okay, remember I told you if it ever says anything about rest or stop, it's 0. In 20 seconds, so there's our time. What is its acceleration? So again, we're going to solve for acceleration. So it's V final minus V initial over time. So I just plug in. So my V final this time is 0 meters per second. My V initial is 10 meters per second. And my time is 20 seconds. Now see, this is where a lot of y'all do it backwards because you'll see, oh, 0 minus 10 is negative 10, and you don't want to get a negative. But we are decelerating, we're slowing down. If you're slowing down, your acceleration is going to be a negative number, and that's just okay. Alright, so 0 minus 10 is negative 10. Negative 10 divided by 20 is negative 0.5. And then remember, the seconds will not cancel because they're both on bottom. So it's going to be meters per second squared. Whoops, oh, I almost forgot my negative in my box. Okay, so if you are slowing down, your acceleration will be negative because you're decelerating, and that is okay. Alright, so if you didn't try this one on your own, try the next one, and then we'll look at it together. So it says an airplane travels down a runway for 4 seconds. So there's our time. With an acceleration of 9 meters per second squared. So they gave me acceleration this time. What is its change in velocity? So this time we're actually looking for the change in velocity. Okay, so instead of writing the VF minus VI to make it look a little simpler, I'm going to write the delta V to mean change in V. Ooh, I didn't leave myself much room. Alright, so A is delta V, or change in velocity over time. But we're going to have to rearrange this formula. We want delta V by itself. So how can I move T to the other side? Well, remember, you do the opposite mathematically. So right now we're dividing by T. So what's the opposite of dividing? Multiplying. So if I multiply both sides by T, these two T's cancel because one's on bottom, one's on top. And so then my delta V equals T times A. So my time times my acceleration. And so then I just plug in. Look. So delta V equals my time, which was 4 seconds, times my acceleration, which is 9 meters per second squared. So 4 times 9 is, of course, 36. Now let's look at these units because I'm super picky about them. We have a second on top and a second squared on bottom. That means 1 second can cancel. So my top one's going to go away, and then I'm just going to get rid of the squared. The squared is going to go away. We're just going to have 1 second on bottom. So the units that I'm left with are meters per second. Okay, so you got to be careful about those units, okay? Getting the units wrong really means you get the whole thing wrong. In my class, I'll just count half off for wrong units, but really, technically, you missed it if you didn't get the units right. All right, so hopefully you got at least one of those right if you tried them on your own. Alright, so now let's talk about graphs for acceleration. So we said on a distance time graph, the slope is speed. Well, on a velocity time graph or a speed time graph, the slope is acceleration. Sorry. So you've got to be careful and look at what your x and y axis are when you're reading a graph. There's a difference in a distance or displacement time graph and a speed or velocity time graph. Okay, so for velocity or speed versus time, your slope is acceleration. Constant acceleration is represented by a straight line, just like constant velocity was represented by a straight line if you watch the section 2 video. A horizontal line represents a constant speed. Okay, so here's our velocity, here's our time. So here we are going 8 meters per second, and notice they just kept on going 8 meters per second. So they're not stopped on a distance time graph. If you see a horizontal line, they're not moving. Okay, but in a velocity time graph, it just means they're moving at a constant speed. If the slope of the line is negative, then the object is slowing down. So this is what's happening. Here our speed is changing, it's increasing, so we're accelerating. Here we have a constant velocity, so as long as we're not changing direction, we are not accelerating here. Here we are slowing down, so we are decelerating. Okay, so if I calculated, of course, I would get a negative number for the acceleration for the downward one. On a distance time graph, acceleration is represented by a curved line. So if you've been watching all the lesson videos, you notice that we said if there's a curved line on a distance time graph, it means velocity is changing. Well, if velocity is changing, that means acceleration is happening. Okay, so here on the distance time graph, we have a steady speed. So as long as we're staying in the same direction, we are not accelerating. We're just keeping a consistent speed. All right, here we're driving a steady speed. We stop because this is a distance time graph. So we're not moving, so maybe we stop for gas. And then here we are driving back to where we started, because if you look, our distance is going back to 0. So that means maybe we left and went to the gas station, stopped, got gas, came back to our house. All right, but if you see a curved line on a distance time graph, that means we are moving. Our velocity is changing, it's increasing in this case, and so if velocity is changing, we are accelerating. You gotta be careful with reading graphs, they get kind of tricky. So instantaneous acceleration is similar to instantaneous velocity. It is acceleration at that particular instance. So it's how fast a velocity is changing at a specific moment or instant. So describe 3 types of changes in velocity. Well, velocity is a change in speed, a change in direction, or a change in both. A change in speed, change in direction, or a change in both. What is the equation for acceleration? Well, acceleration equals v final minus v initial divided by time. We wrote that in the previous slides. What shows acceleration on a speed time graph? Well, if it's a speed time graph, acceleration is the slope. If it's a distance time graph, acceleration is represented by a curved line, and speed is the slope. Define instantaneous acceleration. It is the change in velocity at a particular instant or moment in time. The change in velocity at a particular moment in time. How are deceleration and acceleration related? Well, they are both a change in velocity. However, acceleration is normally an increase in your speed, whereas deceleration normally includes a decrease in your speed. Okay, and so deceleration, like I said, if we plug into the formula, we usually get a negative number for deceleration. Well, not usually. You always get a negative number for deceleration. All right, so let's look at these 2 real quick. Again, if you want to pause and try it yourself, that's perfect. So it says a train moves from rest. So again, there's our initial velocity, 0 meters per second, to a speed of 25 meters per second. So there's our final. In 30 seconds. So there's our time. What is the magnitude of its acceleration? So we're going to solve for acceleration. So acceleration is v final minus v initial over time. So my v final is 25 meters per second. My v initial is 0 because we started at rest, over my time of 30 seconds. So 25 minus 0 is, of course, 25. 25 divided by 30 is 0.83. And remember, since both seconds are in the denominator, it does not cancel. It becomes meters per second squared. All right, so hopefully you got that one. Okay, again, maybe pause, try this one on your own. It says a car traveling at a speed of 25 meters per second, so there's my initial velocity, increases its speed to 30 meters per second, so there's my final, in 10 seconds. So there's my time, what is the acceleration? So again, acceleration is v final minus v initial over time. So my v final is 30 meters per second minus my initial, which is 25 meters per second, over my time, which is 10 seconds. So of course 30 minus 25 is 5. 5 divided by 10 is 0.5. And then, as I've said multiple times, the seconds will not cancel because they're both in the denominator, so we keep both of them. And my unit is meters per second squared. All right. And that is section 3. So hopefully you now, if you watched all 3 of them, you know the difference in distance and displacement, velocity and speed, and then you know acceleration and how to use the formula.